Hello, welcome back to conditioning. So let's start by conditioning on another random variable. So we have a random variable x, and now we want to condition on y. So we are interested like in the discrete case in a probability that looks like this. What is the probability that random variable big X takes the value small x such that, or given or conditioned on basically the event that the random variable big Y is equal to small y? Okay, so here, you just go for the definition of conditional probability. So it's probability of intersection divided by the probability of this guy, and this will make sense if this probability in the denominator is strictly positive. And so we get the probability that big X is equal to small x, big Y is equal to small y. Well, what is this thing? This thing is just the joint PMF of x and y evaluated at small x and small y. And in the denominator, we have the PMF of x. Okay, so basically the conditional PMF of x given y, okay, here will be basically the joint divided by the marginal PMF of y, which is basically the random variable you are conditioning on. And you get this thing which depends on two parameters, small x and small y. Now, to do the continuous case, again, as I said last time, the shortcut is just to take things like this and convert them into PDFs. Okay, so you have a PMF, you convert it into a PDF. So the conditional PDF of x given y, is basically the joint PDF divided by the PDF of y. And again, for this to make sense, it should be the case that the PDF of y, so the values of small y for which this thing is defined are when the PDF of big Y evaluated at small y is non-zero, is strictly positive. Okay, so now we have basically another way for writing the joint distribution. So we can write the joint distribution in terms of the conditional distribution, which simply comes from here. You can just put this there, and so the joint is basically the PMF of y multiplied by the conditional PMF of x given y, like this. Okay, and in the continuous case, the joint PDF can be written as basically the PDF of y multiplied by the PDF of x given y. And you can guess that actually you can write this also as the PDF of x multiplied by f of y given x, like this, which is the conditional PDF of y given x. So this gives you more flexibility. So you can write the joint distribution as now the product of a marginal distribution and the conditional distribution. Okay. So we need the joint, for example, to obtain the marginal. So if you know the joint distribution, how can you obtain the marginal? If you want the marginal PDF of x, then you integrate with respect to the other guy, which is y here. And so now, it is possible that you take this expression and write it as basically the integral of the PDF of y multiplied by the PDF of x given y, the conditional PDF of x given y. And you can write down things like this, even like if you have like sort of a mixed, situation, like if x is discrete and y is continuous. And suppose that you are interested in the PMF of x. Okay, so what is the probability that big X is equal to small x? So now we can mimic this expression here. And we can say, basically, this is the probability that big X is equal to small x given that big Y is equal to small y. Okay, so basically this looks like the conditional PDF here, but it will be the probability that big X is a discrete random variable. So the probability that big X is equal to small x given y, given that you fix random variable y at the specific value small y, and then you multiply by the PDF of y and integrate. Okay, so let's take a concrete example. Now. Suppose that x given y is Bernoulli y. Okay, so let's to make sure that we are on the same page. If I write down something like this, this tilde here, it means that x has the distribution of. So if I write x Bernoulli b, Okay, so this basically means that x is a random variable. It takes the values 0 and 1, 0 with probability 1 minus p, and 1 with probability b. But now I write something like this. I say x and then this vertical bar, and then, I say y. So here I am talking not about the distribution of x. I am talking about the distribution of x given y. And then I put this thing. So here I will characterize this distribution. So I say that it is Bernoulli, y. Okay, so see, it's not just a Bernoulli of some number between 0 and 1. It's Bernoulli y, where y is a random variable that belongs to 0, 1, let's say almost surely, with probability 1. So what does this mean? It means that there are now two random variables. And basically, if big Y is equal to small y, so big Y can take any value from 0 to 1. Let's say that big Y now is like 3/4. Then in that case, given that big Y is equal to 3/4, then X will be 1 with probability 3/4 and will be 0 with probability 1/4. So now X is 1 or 0 with a probability that depends on the other random variable. It's not like a conventional Bernoulli. Bernoulli P is like B is a fixed number, and so it is 1 with a specific probability and 0 with another probability. But now we are not saying that X itself is Bernoulli. We are saying that given Y, X is Bernoulli Y, which means that given Y, if you know Y, if big Y is equal to some small y, then big X as a random variable takes two values, 1 or 0. 1 with probability small y and 0 with probability 1 minus 1. Okay, so this is the meaning of this notation here. Okay, and so from what we know about Bernoulli distribution, this line here that X is equal to 1 with probability small y, I can write it like this: the probability that big X is equal to 1 given conditioned on big Y equal to small y is equal to y. Now, if y, let's suppose that y is uniform 0, 1. So see what is going on here. So it's like X and Y are playing this game. So you generate a random number uniformly from 0 to 1. Okay, so it's like use MATLAB rand instruction. So you will give you a number between 0 and 1, and then the number you get will be the parameter of the Bernoulli random variable X. Okay, so you generate a number from 0 to 1. Let's say that this number is 1/3. Okay, and then you generate X now as Bernoulli 1/3. So X is 1 with probability 1/3 and is equal to 0 with probability 2/3. Okay, and here, if you take Y to be uniform 0, 1 again, this will be the special case. What is the probability that X is equal to 1? So the probability that X is equal to 1, again, let's write it like this. So the probability that X is equal here to 1, okay, is, and you integrate, you have the PDF of Y. So this is the guy that we are conditioning on, and it's a random variable between 0 and 1 almost surely. And then what do we have here? We write here the probability that X is 1 given Y, given that basically big Y is equal to small y. Okay, and this probability, if X given Y is Bernoulli Y, then this probability is equal to small y. And so basically, generally speaking, if we have like two random variables that in which Y is between 0 and 1 almost surely, and it's a continuous random variable with PDF Fy, and if X given Y is Bernoulli Y, then the probability that X is equal to 1 will be given by this integral, and this integral is what? It's nothing but the expected value of Y, right? And it's 1/2 if you take Y to be uniform from 0 to 1. Okay, so now we are basically enriching, our, tools, and we can use basically this conditional thing rather than having the joint. We can basically use the conditional distributions to obtain marginal distributions and so forth. Note that you can generalize. Okay, so if you look here, you can write down the joint distribution of X and Y as, the distribution of Y and then the distribution of X given Y. Okay, so you can basically extend this. It's not difficult to see that this is extendable, and then you can write down the distribution of n guys, like the distribution of x1 times the distribution of x2 given x1, and note that these two guys together, their multiplication will give you the joint distribution of x1 and x2, and then you multiply by the conditional distribution of x3 given the two previous guys, x1 and x2, and then you multiply by the distribution of x4 given x1, x2, x3, and so on. And again, this is, if you recall, one of the early lectures in the course about the properties of a probability measure. There was this chain property, and I think like you proved it in the tutorial session with induction or something like this, and then continuity of probability if you want, like basically an infinite number of events. Here it's the same idea applied to random variables. So the joint distribution can be written as of x1, x2 till xn. You can write it as the PDF. I suppose that our guys are jointly absolutely continuous. You write it as the PDF of x1, then the conditional PDF of x2 given x1, and the conditional PDF of x3 given x1 and x2, then the conditional PDF of x4 given x1 and x2 and x3, and so on and so forth. So sometimes this, this way of writing the joint distribution may be helpful. Okay, then suppose that you have three random variables, x1, x2, x3. They are jointly absolutely continuous, and now they can be conditionally independent. Okay, so we know the notion of independence. So conditional independence of x1 and x3 given x2. So that's the reason it's not. I'm not saying that x1 and x3 are independent. I'm saying that they are conditionally independent given x2. They are conditionally independent given x2. So how do you translate this basically statement here? It means that the joint PDF, the joint conditional PDF of x1 and x3 given x2 can be written as the product of the conditional PDF of x1 given x2 and the conditional PDF of x3 given x2. Okay, so again, if I say that we have those three random variables, they are basically jointly absolutely continuous, and x1 and x3 are independent, are conditionally independent given x2, it means that if you write down the conditional distribution of x1 and x3 given x2, this guy here can be written as a product, as we know from the property of independence. So you can write this guy here as the product, but here it will be the product of the conditional PDFs given x2. So the first guy will be the conditional PDF of x1 given x2. Second one will be the conditional PDF of x3 given x2. Okay. Of course, it's important to note that conditional independence does not necessarily be independent. There was, I think, a homework problem in which, like, there was like a counter example. So if I say that x1 and x3 are conditionally independent given x2, I mean this thing. It's not necessarily true that x1 and x3 are independent, which means it's not necessarily true that the joint PDF of x1 and x3 can be written as the PDF of x1 multiplied by the PDF of x3. This may happen or may not. Okay, so basically the notion of conditional independence does not necessarily imply the notion of independence. Conditionally independent given x2, it just means this thing. Is this thing here? Okay. And so suppose that x1 and x3 are conditionally independent given x2. Okay. So basically, what happens if we write, the joint? So if we don't have this conditional independence, again, you can write down the joint as PDF of x1 times PDF of x2 given x1 times PDF of x3 given the previous guys x1 and x2. So this is general. Okay, so this guy here is general. But if x1 and x3 are conditionally independent given x2, then this third guy here can be simplified and can be written as the conditional PDF of x3 given x2. We can remove the x1. So we get the PDF of x1, the PDF of x2 given x1 times the PDF of x3 given x2, and x1 disappears. And in this case, some of you actually may know this, that in this case, x1, x2, and x3 are called the Markov chain. Okay, so those guys now, they compose a Markov chain, but it's not important for our purposes. And why is this equal to that? Here is the justification. What is the conditional PDF of x3 given x1 and x2? So, I mean, you can generalize. If you can condition on one random variable, you can condition on two of them, not a problem. Definition is the same. Okay, let's revisit the definition. So for two random variables, what is the conditional of x given y? Basically, a fraction, right? So you write down, something over something. Upstairs, the numerator, joint. Denominator, basically the PDF of the guy you are conditioning on. Okay, so this idea, you can basically generalize it. So go back here. So what is the conditional PDF of x3 given x1 and x2? Okay, so fraction line. Okay, then upstairs we have the joint of everything. Okay, so basically it will be the joint of x1, x2, x3, x1, comma, x2, comma, x3. Downstairs, denominator, basically it is the PDF of whatever you are conditioning on. So here we are conditioning on x1 and x2. So here we'll put f of x1, x2, x1, x2. Okay, so this will be the expression. And this is general. This is general. Now you can take this joint PDF here, and you can write it as the PDF of x2. And again, the chain, you can apply it in a number of ways. And here is one way of applying it. You can say that the joint is basically the PDF of x2 multiplied by the conditional PDF of x1 and x3 given x2. Right? You take the PDF of one of the guys, and then you take the PDF of the conditional PDF of the remaining guys given this guy. So here it will be the conditional PDF of x1 and x3 given x2. But now, if we know that x1 and x3 are conditionally independent given x2, we can basically take this conditional joint distribution given x2 and write it as a product. And we can write down this thing here as a product. Okay. And now, what is this? What are these two guys? So let's change the car. So these two guys together. So PDF of x2 multiplied by the conditional PDF of x1 given x2. So that's basically the joint of x1, x2. And it is the same guy living downstairs. So these two guys cancel. Okay, and of course, implicitly, if something is in the denominator, I'm assuming that it is not equal to 0. So these two guys cancel, and you are left with basically the PDF, the conditional PDF of x3 given x2. Okay, and so please spend some time playing with this. Okay, writing down the joint in terms of the conditional distributions and vice versa. It's very useful. It is very useful in applications for probability and statistics. Okay, so. We are still with conditioning, and now we condition on an event. Okay, so last time I did like an event like related to one random variable. So now let's do an event related to two random variables. Okay, so something like this. So the PMF. Let's start with the discrete case. What is the the probability that big X is equal to small x given this event, given that big X is greater than big Y, and X and Y are both random variables. Okay, so again, something that may appear, I personally, you encounter these things, when you do your research. So, what is the probability that big X is equal to small x given this event? Given that big X is greater than big Y, and of course, you can have over, big X less than or equal to big Y, big X, if X and Y are like non-negative random variables, maybe that, that you condition on something like, big X is between Y and 2Y, you can have all those variations. Okay, so again, write down the definition using it. What is the definition of conditional probability of an event given another event? Well, it is a probability of intersection divided by the probability of the guy you are conditioning on. So here in the denominator we have the probability that big X is greater than Y. In the numerator we have the joint event, so that big X is equal to small x. and you know that random variable big Y is less than random variable big X. Okay. Now, so we have our event like this. So big X is equal to small x, and big Y is less than big X. Well, this is equivalent to big X equal to small x, and big Y less than small x. Small x is a fixed number. Okay. So basically, the probability in the numerator is basically the probability of this, that big X is equal to small x, that random variable big X is equal to small x, and then the other guy, random variable Y, is less than small x. And in the denominator, we have the probability that big X is greater than big Y. Okay. So in the continuous case, again, the idea is you basically replace PMFs by PDFs. Okay. So let's focus first on the denominator. Why? Because like the denominator is like interesting in and of itself. You know, what is just the probability of this event? X greater than Y, or X less than or equal to Y, and so on. Again, this probability is a number. You know, the probability that some random variable is greater than some random variable, it's a number. Okay, so this guy here is just a number. And like any event involving two random variables, it's like you have the two-dimensional plane, and you are basically integrating the joint PDF over some region in that plane. The region basically that corresponds to the event. Okay, so same idea. So if you see something like x greater than y, again, if you want like to imagine it, so here is our two-dimensional plane, x and y. And if you have x related with y, like greater than or less than or equal to and so on, it's always good like to have this line here, which is x equals y. Okay. Now, but what is our event? Our event is x greater than y. Okay. So where is x greater than y? So x greater than y is this side here. Right. So for example, this side here, it includes the point 1, 0. Right, and x is greater than y. Okay, so it's this half of the plane, not the other half. Okay, so this is the region in which basically big X is greater than big Y. And so what do I mean by the probability that big X is greater than big Y? I mean, find the probability of this event, this subset of R2. Which, like, if you know the joint PDF, go and integrate the joint PDF over this shaded region. Okay, so in the denominator here, like in the continuous case, what you will do is you take the joint PDF and then you integrate it over the region. And as always, you just need to get your limits of integration correctly. Okay, so what is this region? You are integrating something that is real valued and non-negative. So by Tonelli, you can do the integration any order of your choice. So suppose that we will fix x first at u. Okay, so if x is fixed at u, what is y? Okay, if x is fixed, you are basically dealing with the event in which y is less than x, right? So the integration with respect to y will be from -infinity to u. And you can do this without drawing. You can just say it, right? So, you look at this thing and say, okay, if I fix big X at small u, then I need y to be less than small u. So y will go from its minimum possible value, so generally speaking, this will be like from -infinity up to small u. Okay, so so our integral, and then of course you say, okay, so what are the possible values for u? Well, I mean, generally speaking, it will be from -infinity to infinity. If you have other side information, perhaps x is a non-negative random variable, so the outer integration will be from 0 to whatever. I mean, this will be like in a special case, but generally it will be from -infinity to infinity. So this is basically the probability that that a random variable big X is greater than the random variable big Y, and it will be a number, and it is the integral of the joint PDF over this half plane here, in which corresponds to this event that big X is greater than big Y. Okay. Now, in the numerator, what do we have? So in the numerator, we have a probability that looks like you fix x, right? Fix x, and then you take the probability that y, y is less than x. So here x is fixed. Okay, so we have just one integration here, and this integration is like from -infinity again, because y is less than small x. Then you go from -infinity to x. Okay, and then when you evaluate the integral in the numerator and the integral in the denominator, you end up with something that depends on small x only. Okay, so there is a random variable y, but it is involved here as a random variable big Y. We are not, I mean, this is different from the first slide. In the first slide, we are conditioning that big Y assumes a particular value small y. Here we are conditioning on an event involving both x and y, like x greater than y. So, you know, if you write down something like this, you know, it's a big mistake if you write down your final result like involving some small x and some small y. Okay, you know, you get some small x, some small y if you are conditioning on the random variable, you know, y, assuming one of its specific values. But here we are conditioning on this event, so you end up with something that depends only on small x, and this is true for this case or for the continuous case. Okay, so again, it's very important, like, you know, that you can write down this thing, you know, by reasoning, you know, so just think it, you know, it's not really a derivation here. I'm doing things in a very ad hoc fashion. It's fine, you know, because by the end of the day, I'm really interested in getting you in having you know, you able to compute these things. Okay, we're not like doing a rigorous proof or anything, so you would be able to write down this thing. You should be able to write down this thing like by reasoning, like by you know, such simple reasoning as this. Okay, special case. The guys are basically exponential and they are independent. They are not identically distributed. One of them is exponential alpha and the other is exponential beta. So you just plug in. So again, numerator will be, you take the joint, so the joint will be product of the PDFs because they are independent, and you integrate with respect to y from minus infinity to x. Okay, why is this? Because you are getting the PDF, the conditional PDF of x given x greater than y, so you are basically interested in fixing x and getting big Y less than or equal to small x. And this is the integral of exponential you know, function, so it's very straightforward. And in the denominator, again, this is the event that big X is greater than big Y, which is the integral of the joint PDF over basically the region corresponding to big X greater than Y. And here you know, you go from I wrote it down, so this is a general case with minus infinity, but like in our case here, the indicator functions will tell you it's from 0 because those guys are non-negative random variables. So you start from 0. Okay, and this is an example of the conditional PDF of x given this event that big X is greater than big Y. And as you can see, it depends on a small x. Big Y, you know, small y never appears here, but the joint PDF of big X and big Y definitely plays a role in obtaining such an expression, right? So it is basically the expression, whether in the numerator or denominator, it involves the joint. Okay, but you know, but again, no small y in the resulting expression. You can do things like again, very useful in practice, conditioning on the sum. So you ask yourself, what is the probability that big X is equal to small x given that the sum of big X and big Y is equal to small z? Again, a definition of conditional probability. So this is the probability that big X is equal to small x, big X plus big Y is equal to small z. So we have big X is equal to small x, big X plus big Y is equal to small z. From the first one, big X is equal to small x, so I can rewrite this as small x plus big Y is equal to small z. So this is big X is equal to small x and big Y equal to small z minus small x, like this. Okay, so this conditional probability is the probability that big X is equal to small x and big Y is equal to small z minus small x. Again, what is the value small z? What does it mean? It means that, you know, here we are conditioning on the sum. So for, you know, so somehow we know the sum of two random values. Okay, so we know that X plus Y is equal to some small z. Some small z, you know, this small z may be like equal to 22. Okay, and then we ask ourselves, what is the probability that big X is equal to small x, given that we know that big X plus big Y is equal to 22, or some small. Okay, so now it is again a fraction, and in the numerator we have the probability that big X is equal to small x and big Y is equal to z, small z minus small x. And in the denominator, as typical in conditional probabilities, we have the probability of this event, the probability that big X plus big Y is equal to small z. So again, continuous case, you convert into PDFs. So this will be, this thing here will be the joint probability of X and Y, xz minus x. You replace, so x, small x here, and y, so here you have z minus x. And in the denominator, you have the PDF of the sum. So it's the PDF of x plus y. This is what you have here in the denominator, the PDF of the sum, which we derived in a previous lecture. It is basically the integral of the joint PDF with x replaced by u, y replaced by z minus u, and then you integrate with respect to u, and again generally from minus infinity to infinity. Okay, so again, if we use the exponential random variable, then what do we have in the numerator? So in the numerator we will have the joint with small x and small y replaced by z minus x. Okay, so it is alpha e to the minus alpha x, so it's exponential alpha, and the other one will be it's also alpha here, so it will be alpha e to the minus alpha, but now y I replace it by z minus x, like this. And then again, it's advised that you basically keep track of the range of values using the indicator. So x is greater than or equal to 0, and then y greater than 0, but now we replace y by z minus x greater than 0, like this. In the denominator, we will have basically the PDF of the sum, which is actually the integral of what we have in the numerator with respect to y. Okay, and now if you integrate, you will find that basically x is greater than 0, and from this one we have z is greater than x. So basically, when we integrate, x will be from 0 to x. Okay, 0 to z. Okay, so x is between 0 and z. And you will find that things cancel, right? Because you have e to the minus alpha x, e to the minus alpha minus x. So basically those will cancel upstairs and downstairs, and then we are left with an exponential e to the minus alpha z. But it's also in the denominator. So here we have minus alpha z, and here minus alpha z, and it's like independent of the dummy variable of integration. So this can be pulled outside and cancelled with the one in the numerator. So you end up with just x between 0 and z, and in the denominator you just have the integral of 1 from 0 to z, and this will give you z. So this is nice. So if x and y are actually in this case x and y are IID because they are both exponential with parameter alpha, then if you condition on the sum, so if I give you two IID exponential random variables and I give you the sum of them, I say x plus y is 7. So what is the PDF of x? Conditional PDF of x, given that x plus y is equal to 7. It's very nice. If you look at this result, it means that given that x plus y is equal to 7, x itself is now conditionally, conditioned on the sum. X is uniform from 0 to 7. So you start with two IID exponential random variables, and now you are conditioning. For some reason, you are able to know the sum. So given the sum, what will be the distribution of x now? It's something, it's a different distribution. Again, we are not doing the original distribution of x alone, without like anything, it is exponential. But now I'm asking a different question. What is the distribution of x given that x plus y is equal to z? Okay, and basically what we have here is that x given x plus y is uniform from 0 to x plus y, which basically means that if x plus y is equal to z, the PDF of x given x plus y will be basically from uniform from 0 to z, like this. So this will be over the height 1 over z, okay, and 0 here. And this plays, this result here is very important, like if you study a Poisson random processes. Okay, so something like AMCS 241, when you study random processes, Poisson random process, it's built using exponential random variables, as I said in yesterday's tutorial session, and you basically need a result like this. Sometimes it's very useful. You can solve like apparently difficult problems by basically using this result here, that if we condition on the sum, so if we have the sum of two IID exponentials, if we condition on the sum, each one of them will be uniform, and you can actually, so basically you can repeat this thing for y, and y will be the same. So I mean, I hope that you can actually see this directly, that also y given x plus y will be uniform 0 x plus y. It's the same thing, and actually you can show that they will be independent. Okay, but I'm not showing this here. Okay, so you can condition. I mean, you can condition on an event, you can condition on another variable, you can condition on something like the sum of two random variables, okay, and so forth. And of course, you can use the conditional distributions to compute moments. So now those will be called conditional expectations. So so like if you know the PDF of x, you use the PDF of x to compute the expected value of x. Expected value of x is, if x is continuous, then it is integral x f of x dx. But now we can actually use conditional distributions, and now what we will compute will be conditional expectations. Okay, so you can do something like this. What is the conditional expectation of x given that x is greater than a? So this thing is exactly equal. Okay, so let's do it in slow motion. This thing is, so you do like expectation. So you sum over the possible values of big X, okay, and so you have X here. But now, since this is conditioned on this event, you need to use the probability that big X equal small x, given that big X is greater than E. Okay, so here, conditional expectation, again, like in one sentence, it's, you use the distribution in computing expectations. So now, if you are conditioning on something, you will not use the, the distribution, you will use the relevant conditional distribution. If you want an expectation given x greater than a, then you use the distribution here, the PMF, given that big X is greater than a. And now this thing here, it's it is basically summation x, and this is like the joint x equals small x and x greater than a over basically the probability that big X is greater than a. And then in the numerator, this thing here can be written as the probability that big X is equal to x and x is greater than a, which is simply probability that big X is equal to x, and then you have an indicator. Because you have, this is a fixed quantity, this is a fixed quantity, so basically it's either that small x is greater than small a and we get a 1, or basically small x is less than or equal to small a and we get a 0. Okay, so this was like done in the previous lecture, and here I wrote it directly, but again, this is the line of reasoning that conditional expectation, it is an application of conditional distribution. So write down your basically formula for expectation, but now use the conditional distribution. Okay, in the continuous case, it will be, again, you use the conditional PDF. Okay, and the conditional PDF will be basically, it will be, if I write it again, like it will be integral from minus infinity to infinity x, but then we need to use the conditional PDF of x given x greater than a dx. Okay, and this one is like this expression here, but with using the PDF. So this will be integral from minus infinity to infinity x. This will be the PDF of x, indicator small x greater than a, divided by the probability that big X greater than a dx. So the indicator will make you integrate from a to infinity. Okay, and in the denominator we have the probability that big X is greater than a, and so that's the integral of the PDF from a to infinity, and then we have the integral x f of x, which is right here. But note again that you have integration from a to infinity because of the indicator, and actually we have something in the denominator, which is this probability that big X is greater than big A. So it's the integral of the PDF of big X from a to infinity. Okay. Now, since we can condition one random variable on another random variable, then there is a conditional expectation of X given Y. And so what will be the conditional expectation of X given Y? It is you write down the formula for the expectation of X, but rather than using, basically, if your stuff is discrete, rather than using the PMF of X, now you use the conditional PMF of X given Y. And in the continuous case, rather than using the PDF of X, if you are obtaining the conditional expectation of X given Y, then you use the conditional PDF of X given Y. Okay, and remember what was this thing? This thing was basically the joint divided by the marginal. Why do we divide by X? You mean in the previous one? Okay, I will go back to it. So Fy. Okay, yes, because again, it's because from the very beginning, if you are talking about this probability, we're talking about the probability that big X is equal to small x given that X is greater than A. Right? So, it's our very old friend, the probability that A, two events A and B, this is the probability that A intersect B divided by the probability. So, because you're conditioning here, then you have in the denominator, you have, by the definition of conditional probabilities, you have the probability of X greater than A. Okay, so again, it's like follow your nose, just apply the definition. Okay, so you will have this in the denominator, and then how do we compute this? Well, if your random variable is discrete, then you sum the PMF for the values that are greater than A. And if your random variable is continuous, then you integrate the PDF of the continuous random variable starting from A up to infinity. Okay, so so again, it's because of the conditional. So the conditional expectation, it depends on a conditional distribution or a conditional probability, and the conditional probability by definition will get you those things in the denominator. Okay. So for the conditional expectation of X given Y, again you have the conditional distribution, and again this conditional distribution may be expressed as the joint, and in the denominator we will have the PDF of Y. Now the conditional expectation of X given Y is something that depends on Y. So you conditionally say, okay, what is the conditional expectation of X given that big Y is equal to 17? Okay, so the conditional expectation of X given that big Y is equal to 11. Okay, so your result will vary depending on the value of big Y you are conditioning on. And like if you look at the integral, this is what you expect to find. So, the integration is what? You have the integrand, it depends on two things. It depends on a small x, which is the dummy variable of integration, and it also depends on a small y, which is the value random variable y assumes. So when you do the integration, you will end up with something that depends on small y. You will end up with something that depends on a small y. So this is very important, that generally the expected value of X given Y is something that depends on small y. Again, whether we are doing it for discrete case, if we do the summation, again, small x is the index of summation. But when you do this thing, generally speaking, you will end up with something that depends on this other fixed parameter. You change this small y, you will get different value. And the same thing for the continuous case. Okay, so expected X given Y is a random, it's a function of Y. Okay, so this is very important, keep it in mind. Expected X given Y is a function of Y. So it's a random variable that depends on Y. Okay. Now, let's try to, like, this is one of the very useful, basically, results. So suppose that you have the expectation of X given Y. which generally is a function that depends on y. Now suppose that you take the expectation of this function with respect to y itself. Okay, so let's see this. So here I have the expectation of x given y. What is the meaning of expectation of x given y? Again, if you can close your eyes and what is this thing? Suppose that our stuff is jointly continuous. So what is the expectation of x given y? So expectation of x is integral of x multiplied by the PDF of x. Now this is the conditional expectation of x given y. So we will integrate x multiplied by the conditional PDF of x given y. Okay, so conditional expectation. So you take x, you multiply by the PDF of x, no, the PDF of x given y, the conditional PDF of x given y, and then you integrate with respect to x. So this black thing is basically the expectation of x given y. And again, as you can see from the integral, you do this integral, you will end up generally with something that depends on the value of a small y. Now, you take this thing and you have an outer expectation, and this outer expectation is with respect to y, which means that you will get this thing, which is a function of y. So this thing, you can think of it as g of y. Then you want its expectation by Lotus, the law of the unconscious statistician. You multiply by the PDF of y, and then you integrate with respect to y. So we want now to investigate this quantity here. So what happens if, again, you do the conditional expectation of x given y, and so this is the expectation of x using the conditional PDF of x given y, and this will generally be a function of y. What if we take this function of y, multiply it by the PDF of y, and then integrate? So what if we take this function of y and take the expectation with respect to y? Okay, so we have this double integral. And the order of operations is simply that you do the inner integral first with respect to x, which means that you compute the expectation with x given y, and then you integrate with respect to y. But then you will go back to here. Then what? So what if we can actually interchange the order of integration? Okay, so of course this is not generally true, but actually this will be true. We are able to interchange the order of the two integrals, basically if x has a finite first moment. Okay, so if basically the expected value of absolute x is infinite, which means but also that expected x is less than infinity, then actually we can interchange the order. Let's see why. So this thing is less than infinity. Okay, so what is the expectation of the absolute value of x? Well, it is as usual. There is no conditioning here or anything. You take absolute value of x, multiply by the PDF of x, integrate with respect to x, right? But what is the PDF of x? What is the PDF of x? Well, the PDF of x is basically you can obtain it from the joint PDF of x and y, and you integrate over y, right? So if you integrate the joint of x and y with respect to y, you get basically the marginal distribution of x. So this quantity here is this double integral. Okay, now this quantity here is nothing but the expected value of absolute x. So if the first moment of x is finite, which corresponds to the case in which the absolute first moment is finite, then you know that this integral here, this double integral involving, let's see what we have, absolute value of x and the distribution of x given y and f of y, this integral will be finite. Okay. So now we can apply Fubini. So again, let's go back here. Suppose that you want to investigate whether it is valid to interchange the order of integration here. So what does Fubini tells you? You do the following check. So Fubini tells you that you check the integral, okay, but with the magnitude. Okay, so everything that is that can be positive or negative, you need to take the absolute value. So you need absolute x, and then PDF is non-negative, so it can remain as is. Okay, and then you have f of y, and then you have dx dy. So you check this thing with an absolute value. If it's finite, if this thing is finite, then by Fubini, what you can do is, now this original integral without absolute value or anything, it can be done in any way of your choice. You can do the integral first with respect to x, then y, or y then x. Okay, so in our case, if we assume that x has a finite first moment, then actually this integral here will be finite, and so by Fubini we can actually interchange the order of these two integrals. Okay. So what we will do now is that we will integrate first with respect to so this is the original thing, okay, which means that you integrate first with respect to x, then with respect to y. But by Fubini, actually you can integrate first with respect to y and then integrate with respect to x. Okay, so see this integral with respect to y. So so now x will be alone outside. We'll do the integration with respect to x last now by Fubini. Now what is this thing? What is this thing? So it's the conditional PDF of x given y multiplied by the PDF of y. So basically this is the integral of these two guys multiplied together give you the joint. Exactly, this will be the marginal. It's the, these two guys, the product is the joint, and once you integrate the joint with respect to y, you get the PDF of x. And then now you have x multiplied by the PDF of x. And this is the expectation of x itself. It's the expectation of x itself. Okay, so if x has a finite first moment, actually the expectation of x can be computed using this way, in which you take the expectation of x given y, the expectation of x given y, which will be generally a function of y, and then you take the expectation with respect to y. Okay, so again, this one here is like, it's x f of x dx. Now this one here, it's like you compute the joint, so x given y, and then you integrate with respect to x, and you end up with a function of y, and then you multiply by the PDF of y, and then you integrate. Okay, so if the first moment of x is finite, then we have this equality here. And you may actually, you may think that this is like sort of nonsense, because just compute the expectation of x. If, look at this thing, it's like, even like in terms of integrals, this is like double integral, this is like one, integral. Contrary to what you may believe just by looking at the expressions, in many cases, actually, this is the way to go in computing the expectation of x. Okay, so using this, it's called iterated expectations. Okay, so it has several names. So this is called iterated expectations. Or some people call it the tower principle, or the tower method, or principle, or whatever you want to call it, which is you want to find the expected value of x. You go and find the expected value of x given y, and then you find the expected value of y, which again may seem like something that is like convoluted, but actually it's the way to go in some problems, as we will see. And you can generalize this, by the way. So if you have a function of x with a finite first moment, then you can obtain this expectation by doing what may seem to be like, what is this? So you do the expectation conditionally on y, and then you take the expectation with respect to y. And definitely this needs an example to like see a situation, at least one situation in which this is what I want to say, like very useful. But before doing this, since we are iterated expectation, let's first like take like sort of another idea about computing the variance. Okay, so so from the previous slide, we have like equation of x can be done in this weird way. Okay, expectation y. And again, if it confuses you, write down a subscript telling you what you are doing. So it's not bad, especially if you are new to these things, to write down that this is x given y and this is y. To remind yourself that the inner expectation, you will use the conditional PDF of x given y if the guys are jointly continuous, and then the outer one you will use the PDF of y. Now what about the variance? The variance has this formula here, okay, which it's called the law of total variance, which is like, again, it looks complicated, but it's useful, as we'll see. But let's derive this formula. Okay. So what is the expectation of variance x given y? Okay. So what is variance x given y? You know, the trick again is like, don't treat these things as if they are fundamentally new. They are the stuff that you know, but you use the conditional distribution. So if I write to you the variance of x means expected x squared minus expected x squared, right? So, and like if you compute these things with PDF, then you multiply by the PDF of x. When I say variance of x given y, I'm saying you do the computation of the variance, but now rather than using the PDF of x, go and use the conditional PDF of x given y. Okay, so the variance of x given y, again, it may look something like scary, but it is this thing. It's the expected value of x squared, and here we have the expected value of x squared, but everything is given y. Okay, so let's write this alone. So the variance of x given y is equal to. Now, if you just talk about the variance of x, then it is expected x squared, right? And then here there is expected x, and then you square. Now, since you are conditioning y, you just mean the following. You are not computing, these expectations using the PDF of x, if x is continuous, you are conditioning on y. You are conditioning on y. So basically the variance will be this thing minus this thing squared. Okay? So this is the meaning. And then you take the expectation with respect to y. So it means that, you basically take this variance, and then if things are continuous, you multiply by the PDF of y, and then you integrate. So what is this thing? Expectation is a linear operator, so expectation of two things. It's the expectation of the second term. We will just leave it as is. Okay, it looks very weird. Just keep it as is. But what is this? What is this? Expectation y, expectation x given y, x squared given y. What is this thing? I'm taking the expectation of x squared given y, and then after that you will get something that you may generally depend on y, and then you will get something that depends on y. You multiply by the PDF of y and integrate. So what is this thing? It is what I have on the previous page. Okay, but not a bad idea actually, to imagine that the guys are continuous and see what these things actually mean. So this guy here is integral x squared f of x given y. Okay, x given y dx. This is the conditional expectation. Okay, so write down the formula for your expectation, but rather than using the PDF, use the conditional PDF, and then you use the PDF with so you multiply by the PDF of y, and then you integrate with respect to y. Now, if this expectation x squared is finite, then you can use Fubini. But actually, in this case here, you do not need Fubini. You can use Tonelli, because x squared is guaranteed to be non-negative. So actually, the double integral here, you can do it in any order, and if in one order you get plus infinity, the other order will also give you plus infinity. So here, actually, because the function of x is non-negative, we can just appeal to Tonelli, but it doesn't matter. So we can interchange the order, and so you will basically do the integration with respect to x at the end, and then you start with the PDF, with the stuff with y, and so these two guys together give you the joint. And when you integrate the joint with respect to y, what do you get here? You get f of x, you get the marginal of x, and when you multiply the marginal of x by x squared and integrate, that's expectation x squared. That's expectation x squared. Okay, so the first term here will be expectation x squared. Again, don't forget from the previous page that expectation g of x, is you take g of x given y, and then you do an outer expectation with respect to y. The inner expectation, you use the x given y. Okay, and this is granted that the expectation of g of x is a finite number. Okay, so variance of expectation x given y. So expectation x given y is a function of y, and so we can compute its variance. And so what is its variance? Well, the variance is, the variance of any quantity, so the variance, what is the variance of a function of y? What is the variance of g of y? Well, variance is variance. It is the expectation of the square of the thing, okay, minus you take the expected value of the thing itself, and then you square it. Follow the definition. Okay, so is the variance of expected x given y? So variance of expected x given y, well, it's this thing squared, and then you take expectation with respect to y, and then you take basically the expectation, and then you square. Now this again leave as is, okay? But then what is the other thing? If we look at the other thing, if you take expectation x given y, and then take the expectation with respect to y, what is this thing by iterated expectations? This is what we proved, that this is expectation x, and then you square. Okay? And so now, so again, this is like, again, you play with these quantities, and I highly recommend that you write down these things. You repeat, keep writing down these things from mind till you feel you really understand what each term means and why we get this. Very, very important. Okay? So now we have those two guys, add them. When we add them, the mysterious, basically terms, those guys will cancel out because one appears here with a minus sign, here with the plus sign, and then you get expected x squared minus expected x squared, which is the variance of x. So the variance of x is, basically expected the variance of x given y plus the variance of expected x given y. Again, you may say, oh, this guy is like cute, and we can just use it, but in fact, there are some problems that cannot be solved except by computing the stuff on the right-hand side. Okay, so this is called the law of total variance. So let's see, like, sort of the example that hopefully will show you why basically iterated expectations, or like you want to compute something related to x, but then you basically invent this y and you do things conditionally, and then you basically like compute variance with respect to y, expectation with respect to y, and so on. Okay, so here is like sort of the classical example. So we have the x's are IID random variables. Okay, and then we have a sum of them. So far so good. But now here is the new thing. The number of terms in the sum is not fixed. The number of terms in the sum is not a fixed number. The number of terms in the sum is itself a non-negative integer valued random variable. And for simplicity, let's take that this is independent of the x's, and that every guy here has a finite second moment. Okay? So this is a situation that is, again, perhaps maybe new to some of you, that you are summing random variables, but you don't have like, 3 of them or 4 of them or something like this. You have n of them, and n of itself is like, is like something, is something like a random variable itself. So question, what is the expected value of S? What is the variance of S? Now, if n is fixed, if big N is fixed, computing the expected value of S and the variance of S is sort of very straightforward. So let's do it on the side. So, okay, so if N is fixed, or like let's say n equal to, let's say, c almost surely, c is a constant integer. Okay, then what is expected S? Well, expectation is linear, and so this thing will be I from 1 to c expected, xi, All the guys, they have the same distribution of some random variable x, and so basically this is the expected of x multiplied by the number of terms here that you have in the sum, which is c. What is the variance of big X? Now you know that the variance of a sum, variance is not linear, and the variance of a sum typically is a double sum of the covariances. But if the guys are independent, then they are uncorrelated, and covariance xi xj for I not equal to j will be 0, and in that case the variance will be a sum I from 1 to c, the variance of xi. So again, it is c. It is the variance of one of the guys multiplied by the number of terms here. And again, here it's some variance of sum of variances. Again, here I am saying, what if n is a constant? If n is a constant, then things are very straightforward. It's like exercises you have been doing. Expectation of the sum is sum of expectations always, because expectation is linear. And because the guys are identically distributed, just take the expectation of one of them and multiply by the number of terms. And if you are talking about the variance, since they are independent, they are uncorrelated, so variance of a sum is sum of variances. They are identically distributed, so take the variance of one guy, multiply by the number of terms, so it is the variance of x multiplied by c. This is if n is equal to a constant almost surely. But the problem tells you that n is a general non-negative random variable. In other words, that n can be 2n with a certain probability, 3 with a certain probability, 4 with a certain probability, 17 with a certain probability, 1 trillion to the power 1 trillion with a certain probability, and so on and so forth. How can we find the expected value of s, of the variance of s? So basically, the ideas I have just discussed are basically the tool. So you want to basically find this expected value. So the trick here is to condition on n first, right? Because like if you condition on n, if you fix n, things are very straightforward. So this is the trick. If you want the expected value of s, so it is the expected value of this thing. It doesn't matter, n is any non-negative integer. If n is equal to 0, then the summation is from 1 to 0, which by convention means that the summation is 0. N can be 0, 1, 2, 3, 4, 5, 6, 7, 8, till infinity. It can be a Poisson random variable, a geometric random variable. It can be any of those discrete random variables that take non-negative integer values, anything. Okay, so here is the trick. So you want to compute this expectation, right? Condition on n first. Condition on n first. Treat n as if it is a constant. Okay, so condition on n first, and then you will get something that depends on n. Then you have an outer expectation that depends, that with respect to n. Okay, so it is the concept of iterated expectation. So again, iterated expectations means that expectation A is expectation A given B, and you use here the conditional of A given B, and then you do the expectation with respect to B, right? This is basically the idea of the previous slide. Do it. So here, do the expectation fixing n, then generally you will get something that depends on n, then have an outer expectation with respect to this n, and you will get your result. Okay, so now if you fix an n, what is the expectation of this guy? It's the argument that I did here. If n is fixed, if n is just a number, a number that, if it's a degenerate random variable that is equal to a constant almost surely, then the expected value of the sum is the expected value of one of the x's, because they are identically distributed, and you just multiply by their number. So by iterated expectations, to find the expected value of s, you still need to do an outer expectation. No, n is not a constant. N is a constant when you do the inner expectation given n. So again, it's expectation. The inner expectation is given n, fixing n. So when you do the inner expectation, n is treated as fixed. But then there is an outer expectation that will account for the fact that n is not fixed, n is a random variable. So this is the beauty of conditional expectation. It is something like this. You want to compute the expected value of A. Okay, so you do first expected value of A given B. When you do the expected value of A given B, B is treated as a constant. B is treated as a constant, and you use generally the conditional distribution of A given B, and B is treated as a constant. Now once you are done, you get something that depends on B. Then you need to take an outer expectation with respect to this thing that initially you have assumed to be constant. So this is the story here. Again, you do, and so n, you take the expectation, you do something like this: s given n and then n, s given n and then n. In the inner expectation, n is treated as fixed, and so this is like sort of the old stuff that you know. The expectation would be the number of terms, now treated in a temporary way as fixed. This is not some, n, I know that n is random variable, but here in the inside expectation, it is a conditional expectation given n. So n is treated as fixed. Okay, and then you, basically the expectation of the sum given n is n multiplied by the expected value of one of the guys, and then, oh, n is a random variable, then you apply expectation. Now expected x is a constant, you pull it outside, and then you take the expectation of n itself. So the expectation of s is the expectation of x multiplied by the expectation of n by iterated expectations. Okay, variance, same story. Okay, so let's see. So it's a bit more involved because the variance of x now it has two terms, but again we will see that it is not that difficult. So what is variance of s? So S is this annoying sum. It's a sum involving a random number of terms. Okay? Why expected X is not, I don't understand. Expected X is a number. It's the mean value of those random variables. Expected X is a number, 7, 25. Okay, so, when you fix N, the expected value of the sum will be the expected value of one of the guys because they are identically distributed, and then you multiply by n. This expected value of x is a constant. You pull it outside, and then you have expected n itself. Okay, so same story, but now you apply total. No problem here. Total variance. So total variance is a bit more demanding. So for total variance, it tells you need to do the variance given n, and then you need to do the first moment or the expectation given n. So again, the first steps will be steps in which we pretend that n is not a random variable because we are conditioning on n. We are treating n as fixed. And then we remember that n, and then we recall this fact, oh, n is actually a random variable, and then we do the expectation or the variance with respect to n. But the inner expectation or the inner variance, this is the beauty of it. The inner expectation or inner variance is done fixing n, treating n as if it's a constant. Okay? So, now, what is the expectation of the sum given n? Well, it's the expectation of one guy multiplied by the number of terms in the sum, which is treated for now as a constant. Okay? What is the variance of the sum given n? Well, if we fix the number of terms in the summation, this is the variance of a sum. Generally, the variance of a sum is not sum of variances, but because the x's are independent of n, and because the x's are independent of of one another, then the variance in this particular case, the variance of the sum is the sum of variances, and so since the guys are identically distributed, it's the variance of one guy multiplied by the number. Are we done? Not yet. So in computing those inner expectations or inner statistics, expectation and variance, we are dealing with n as fixed, but we are not done yet. Now you need to take this guy, you need to take the expectation with respect to n. What is variance of x? A number. Variance of x may be 1. Okay, it's a number. You take it outside and you are left with the expectation of n. Here we need to take the variance with respect to n. So remember, the variance of alpha multiplied by a random variable a, it is alpha squared, the variance of a. So the expected value of x is a constant, but we are computing the variance. So this constant will appear outside the squared because we are computing the variance of a constant times a random variable, and then you have the variance of n. So the variance of s is basically the sum of two terms. The first term is the expected value of n times the variance of x. The second term is the expected value of x squared. So it's the expected value all squared. Then you multiply by the variance of n. Again, this seems like a mission impossible if you try to deal with s directly. Dealing with s directly, who knows? I mean, what is the distribution of s and so on? Later in the course, when we study the characteristic function, we will actually compute things like the distribution of s, at least in some special cases. But if you want just the first and second order statistics of s, I mean the first moment and the variance, then iterated expectations and the law of total variance are your friends. Because, again, here you do your stuff in two steps. In the first step, you fix the number of terms in the sum, and then it's the stuff you have been doing, since whatever day in your life. And then you need to have the outer expectation or the outer variance, and in this step you treat n as a random variable as it is. So this again a classic example for using iterated expectations and the law of total variance, and you will see stuff like this in the homework. Okay. It turns out that the conditional expectation of x given y, it has a meaning. So remember when I talked about, the first time we studied variance and, first moment, I said that the expected value of x is your best guess regarding random variable x if you want to make a guess with a constant and you want to minimize the mean squared error. So it turns out that the expected value of x given y may have a similar meaning. Okay, so now we are in this very important topic, which is called minimum mean squared error estimation. And let's actually, go for the general case from the very beginning. So let's suppose that x and y are not, each one of them is not just a random variable, but that each one of them is actually a random vector. Now, if this is making you unhappy, just imagine that x itself is a random variable, x1 and y is y1, and ignore the rest till you basically swallow the argument. Or, you can just take the general case first. Okay, so we have now a random vector x composed of those n random variables from x1 to xn. And we have another random vector y composed of the random variables from y1 to yk. Now, suppose that you observe y. So you know the y's. Okay, so vector y is a vector of measurements, things that you measure and know, or observations, or whatever you want to call them. Okay, now you ask yourself this question. Given those observations or measurements, given vector y, can I make a guess regarding vector x? Which means that you need to make a guess regarding x1, x2, x3, up to xn. Okay, so we want to build an estimator. And the estimator is a function of the observations. So basically we want a function g1 that takes the observations, here in our case are y1, y2 up to yk, and this function takes those k observations or k measurements and spits out an estimate, a guess for x1. And then we want the function g2 that takes the observations and gives you an estimate for x2 up to gn, which again depends on the k observations, and basically gn of y1, y2, yk should give you some guess, some estimate for xn. Okay, so this is our beginning of talking like more seriously about estimation. So estimation is like this. Okay, so you have observations, you have measurements, you have stuff that you know, and you want to use this stuff to estimate, to make guesses regarding stuff that you do not know. Okay, and so you want to build estimator functions or estimators, and so those are functions that depend on the observations, and they map the observations to guesses regarding the random variables x1 and x2 and till xn. Okay. Now, how do we build those functions? How do we build those g functions? Okay, what should they look like? So are they like the sum of the observations? So is like g1 the sum of the y's? G2 the product? Or, you know, so are these like arbitrary functions, or do we need like to design them like to make the estimation, you know, good in some way? Okay, so minimum mean squared error estimation is this idea in which we will design those functions g1, g2 up to gn to minimize the minimum mean squared error. Okay, so this is the idea. The idea is that we have vector x that we want to estimate. We apply g of y, so that's a function applied to y. You know, this appears abstract. What I mean by this thing is basically this. Basically, this function of vector y is basically n functions. N functions. Each of them takes the k observations or measurements and gives you a guess regarding you know, random variable x1, random variable x2, and so on. So what is the difference between x and g of y? You can say that this is like the error in your guess, the error in your estimation, right? What this thing looks like is a vector. The first element will be x1 minus its guess, which is a function g1 applied to those observations. The second element will be x2, your second random variable of interest, and minus its guess, which is some function g2 applied to the k observations, and so on. So we have a vector, and each element in a vector basically is an estimation error. It's the difference or discrepancy between a random variable x and its estimated value using the observations or the measurements. So now, how do we design the g functions? There are several ways, several plausible ways for doing so. Minimum mean squared error estimation relies on the following idea. So you take basically the L2 norm squared of this vector. Okay, so what is the L2 norm squared? It will be summation j from 1 to m, and then we have random variable xj minus its estimated value. And what is its estimated value? It's some function gj applied to the observations squared, right? So the L2 norm squared of a vector is basically the sum of the squares of the components. And so you take each error squared and then you sum over all the components. Okay, so this will be the inner quantity here. So this is basically the L2 norm squared. And so what we will do is that we will obtain those functions g such that the expectation of this thing given y is minimized. Okay, so this is the idea of MMSE. It's not the only idea in estimation. There are so many ways of designing estimators. It's one of the plausible ideas, and it is very useful also to know and understand. Okay, so minimum mean squared error. So from its name, squared error. So error, I mean, you can basically understand the letters in reverse. Error, E. Error means a difference between, the thing that you want to guess or estimate and the estimator. And by estimator, I mean a function that you apply to your observations or measurements to generate the guess. So the difference between your estimate and the true thing is basically an error. So you talk about square error. Okay, which means that you don't care about the sign of the error. You don't care whether x is greater than g or g is greater than x. You don't care about the sign, and so you square. Okay, you take the error square, and then you take the mean, which means that you apply expectation given y. Again, we are conditioning on y because we are basically playing this game, assuming that we have access to a set of observations, of measurements. Those are y1, y2 up to yk. And so those are assumed now, for now, to be known numbers. Those are what you get when you do your experiment or you use your measuring, your measuring devices or whatever. Okay? So mean squared error, and then you minimize. So this is the idea of minimizing the mean square error. Obtain the function g, and actually g is not just one function. We have those big N functions. Obtain the g's such that this expectation, this conditional expectation given random vector y is minimized. Okay, so that's minimum mean squared error, MMSE. Okay, and this is basically the function that we minimize. Okay, again, each component here is some xi, and we have n of those guys, minus its estimated value, which is a function gi applied to y1 to yk, which are assumed to be given, and then we square, we take the expected value, and then, let's now find the g's that minimize this, minimize this quantity. Okay. So, obtaining those g's is interesting, is very, very interesting, and it's highly recommended actually that you know it, but, it's optional. Okay, so in the notes on MMSE, you will find basically the derivation. How do we obtain those g functions? Okay, but to be able to solve the problems and proceed in this course, you may ignore the proof and just take it for granted that the functions g that minimize the mean squared error are the conditional expectations of the x's given the y's. Okay, so again, you can prove that if you solve this optimization problem and you obtain the g functions that minimize the mean squared error, that basically the first function g of 1 is simply the expected value of x1 given y1, y2 up to yk. The second function is go and compute the conditional expectation of x2 given y1, y2 up to yk, and so on. So the solution to this problem, your best estimate in a minimum mean squared error sense is the conditional expectation of x given y.